So we will look at various other kinds of stochastic processes, so that you will understand thoroughly what it actually means.
Okay, sir. Okay.
But mostly we will be looking at discrete time, but well, both discrete and continuous, but we will not look at, for example, Brownian motion and this Wiener process and these kind of things in great detail. Maybe we will touch upon it, but not discuss in great detail.
Okay, sir. Okay.
Okay. Himanshu, you have any questions?
No, sir.
No. Nitish?
No, sir.
Okay, anyway, Savan, if you have any questions, you should have asked me last year. Jayant,
Sir,
you have any questions?
sir, regarding stochastic process, sir, will stochastic process should be defined only on the common probability model, sir? We are two, let's say, consider two different experiments.
Generally, it's you have to define it over the same probability model. Okay, when I say same probability model, I mean same omega and f.
Okay.
Okay, the probability measure could be different, but the underlying omega should be the same.
Okay.
Okay. Any questions, Ayush?
Yes, sir. Sir, I have a question.
Yes.
So basically, the thing, like, there should be a sample space of head and tail, and sir, we can say that probability of head is, say, for biased one 1/2, and probability of tail is also 1/2. So, sir, using random variable, we have mapped head to 1 and tail to 0.
Correct.
So, sir, calculating the probability, we are not using like any notion of random variables here.
Exactly.
So why are we defining random variables in that case?
So essentially, yeah. So for example, one use case would be, let's say you have been talking about head or tail, right? And subsequently, I can ask a lot of questions related to that, right? So for example, if I toss n times, what is the probability that I get k heads? What happens if to the ratio k over n and all that, right? You can ask a lot of questions related to that. And likewise, for example, I'm studying some weather data and I want to look at whether it's going to rain or not going to rain, okay, every day. So that is also by binary, right? Yes or no, 1 or 0, right? But the underlying probability, the way you compute or estimate the probability would be different. The kind of experiments that you do, everything would be different. But the moment you map omega to R, right, 0 and 1, and you start dealing with random variables, you can sort of forget about what the underlying experiment is. The entire theory can be built without knowing what the underlying experiment is. I'll call it as Bernoulli random variable and move ahead. Right?
Okay. Okay. So this is sort of generalizing any experiment to one common point.
Exactly. So I need not see Gaussianity, right? So Gaussian random variable, it could describe noise, for example, in your receiver or a phone, or it could describe some other things in your. Let's say you collect some image data, the noise there could be again Gaussian. So it doesn't matter what experiment are you looking at. It sort of abstracts out the underlying experiment or the uncertainty that you are trying to model. So just look at Gaussian, right? In simple words, you need not write some 100 textbooks on various experiments. You can just write one textbook on probability theory, which can be used to describe many experiments. The way that gets enabled is through random variables. Okay?
Okay.
Okay. So let's continue with whatever we are doing, whatever we started in the last class. So we started looking at what is a stochastic process. So the way I defined is, you just take a map xt from omega to r, t belonging to some index set I. So if this could be countable, or it could be uncountable. So if it is countable, it's called a discrete time stochastic process. Stochastic process, I'll call SP for short. If it is uncountable, it's called continuous time stochastic process. Okay. So we started looking at one example, which is the following. So it's called a Bernoulli process, right? So let's look at the example, which is a Bernoulli process. I hope you remember what Bernoulli process is. So essentially, what you do is you take a sequence of binary random variables, okay, Z1, Z2, etc. IID binary or Bernoulli random variables, okay. Say P is the probability of head to occur, or let's say Zi is 1. Okay, of course, Q I'll define it as 1 minus P, which is the probability of Zi equal to 0. This is true for all I, okay, because it's IID, right? IID means independent. That is, if you look at the event Zi equal to 1 and Zj equal to 0, those two events are independent, or in fact for every ij, right? It's not just pairwise. You can take ijk, Zi, Zj, Zk equal to something. They're also those events are also independent. Okay, so this is called a Bernoulli.
Sir?
Yes.
Sir, here Zeta is equal to 1, it just means the occurring of Zeta, no, sir? Like,
So
sir,
Zeta
if we
equal
just
to 1 essentially means that it is all those outcome which gets mapped to 1 under Zi is an event, right? By definition.
okay,
So
sir.
let me write this. So what is Zi equal to 1 mean? It is, or the meaning of this is, it is all those outcomes which gets mapped to 1. This is an event, right? Belongs to F. Why?
Okay,
because
sir,
I can write this. I'll just write this in detail. Maybe it's good. This is nothing but is less than or equal to 1, right? This should happen intersection set of all omega in omega such that Zi of omega is greater than or equal to 1. So I can write this as 2 events, right? This is obviously in F because this is by definition of a random variable. This should belong to F, right? This is nothing but all those omega Zi of omega less than 1 complement. Do you agree?
yes, sir.
So this also belongs to F because why? Do you know why?
Because, sir, if A belongs to this, then this complement also
First
belongs
under
by
complement.
axiom, sir.
No, the first one we don't know whether it belongs to whether it belongs to F, right? Because by definition this belongs to F, but we don't know whether this belongs to F. Okay, now let me. This is an aside. Since you asked, I am telling you. So this is set of all omega in omega. Zi of omega less than 1, right? I can write this as. So let's look at this. Okay, so set of all omega in omega such that Zi of omega is less than or equal to 1 minus 1 by n. Sorry, 1 minus 1 by n. So for example, n is equal to 1, this gives me 0, right? Zi of omega is less than or equal to 0, that is Zi of omega equal to 0. If I take 2, it will be half, it will take 3, it will be, and so on. I'll take the union of all the set. Do you agree?
Yes,
Do
sir.
you agree that the left hand side is same as right hand side? Because you take an omega on the left hand side, you prove that it's there on the right hand side. You take an omega on the right hand side, you prove that it's there on the left hand side, right? Do you agree? That's how you prove that these two are equal. Do you agree
Yes,
that these two are equal? Any questions?
yes, sir.
Okay. So that means this is by definition belongs to Fy. It's of the form all those omega such that Zi of omega is less than or equal to some x. X here is 1 minus 1 by n. And I'm taking countable union of sets in F, therefore this should also belongs to F, right? That means this set belongs to F, and therefore the complement should belong to F because F is closed under complement, and therefore the entire thing is in F. So therefore, I can talk about the probability, right? So probability of Zi equal to 1 is nothing but probability of this, which is nothing but P, right? So probability of Zi equal to 1 is P. Is this clear?
Yes, sir.
Okay. So I have taken a stochastic process or a Bernoulli process, Z1 through Zn, and I will construct a sample path or the Bernoulli stochastic process as follows. Okay, so let me just write the picture, and then we can define it later. How? What do you mean by that? Okay, so now at 0, what I will do is I will again look at what is Z1. Okay, if Z1 is 0, I'll remain at 0 till 1. Okay, and again I'll look at Z2. If Z2 is also 0, I'll remain 0 till 2. And then I will look at Z3. If Z3 is 1, it will go to 1. Okay, and at 3 I'll look at Z4. If it is 1, I'll go to like this, and then continue like this. Okay, you understood what this is, right?
Yes, sir.
You agree? You know what this is, right? Okay. Now this is so if you look at any time instant, right? So for example, you take any time instant t, there is some amplitude, right? I can define this as your xt, for example. This is a random variable. It can take 0, 1, 2, 3, and so on, depending on how you have, depending on the outcome corresponding to Z1, Z2, Z3, and so on. Okay. Now, let me call this as x1. You can think of this as, people arriving at a counter, right? Ticket counter. So what I will do is I'll toss a coin. If it is a tail, nobody comes. If it is a head, then one person will come. Okay, and then again I'll toss. If it is a head, then again another person will come, and so on. Right? This is the arrival process that I'm looking at. Okay. Okay. So now this is, let me call this as x1. This is called the first arrival time, right? What is this called? X2. This is the arrival time of the second guy when first guy has already arrived, right? And this is x3. Okay, I get a sequence x1, x2, x3. Okay, now let's try to analyze what is x1. Okay, so what do you think is x1? So this x1 will be 1. When will x1 be 1? That means in this case x1 is 2, right? Here it is 2. But when will x1 equal to 1?
So when first arrival is at 1, sir.
Yeah. So basically x1 is 1 if I can say z1 is 1, right?
Yeah.
If and only if z1 is 1, right? Because something should have appeared here itself so that you get a 1 here, right? So z1 is equal to 1. Do you agree? So that means the probability mass function of this being 1 is nothing but probability of z1 equal to 1, which we know that it's equal to p, right? Is this fine? Okay. Okay, now let's look at x2, right? So, sorry, x1 equal to 2. When will x1 equal to 2? This will be true if and only if the first time nobody should appear. Sorry, this is not x1, z1. z1 should be 0 and z2 should be 1, right? Is this clear? So, what will be px2, px1 of 2? This is nothing but probability of z1 equal to 0 and z2 equal to 1. z1 and z2 are independent, so I can split. So probability of z1 equal to 0 is 1 minus p. Probability of z2 equal to 1 is p. Fine.
Yes, sir.
Okay. So if you continue this way, right, I can ask what is probability of x1 equal to some j. When will this happen? This will happen when you get continuous zeros, right, till j minus 1, and you get a 1 at j minus 1, right? So that means the probability that, so the probability that x1 equal to j is nothing but the probability that z1 is 0 and z2 is 0 and z3 is 0 and so on, zj minus 1 is 0 and zj is 1, right? So that's nothing but 1 minus p power j minus 1, and in the jth one you should get a head, right? So here j is greater than or equal to 1. Is this fine?
Yes, sir.
So okay. So any random variable whose PMF is given by this, let's say 1 minus p power j minus 1 times p, this thing is called a geometric random variable. Okay. This distribution is called geometric probability mass function. Okay. For example, if Z1, if you look at it, it can take either 1 or 0 with probability p and 1 minus p. It's called a Bernoulli random variable. This is called a geometric random variable, and the PMF is given by this. Okay. Everything fine, right?
Yes, sir.
Okay. Now let's look at what will happen. Yes.
Hello.
Yes.
Sir, can you again explain this, sir? Like I didn't understand.
Okay, so let's go back. So you understood how am I generating this graph right here?
Yes.
So essentially I toss a coin. If it is head, I will put a 1, otherwise 0, right? So for example, in this case, I got a tail, and then I got a head and so on. Okay, this is what it is. That means Z1 is 1, Z1 is 0, Z2 is 0, Z3 is 1, and so on. Okay. Now, the inter-arrival times, I'll denote it by xi. For example, x1 will tell you the time at which the first person arrived at the queue or the first head appeared in the sequence of tosses. Okay. X2 will tell me the first head appeared after the first previous head, right? So the second head appeared, right? And so on, the inter-arrival times. Is that clear? Hello?
Yeah, this one.
The definition of x1. So,
Yes, sir, yes, sir.
so when can you say that x1 is 1? X1 will be 1 only when z1 is 1, right? Because if z1 is 1, if you draw the picture, this is 0. If z1 is 1, you will get 1 here itself, right? Do you agree?
Yes, sir.
So that is why x1 is 1 if and only if z1 is 1. So that means probability of x1 is 1, which is the PMF, is nothing but probability that z1 is 1 and you get p, right? When will x1 equal to 2? That means you should get, the first outcome should be a tail, that is z1 is 0. The second outcome should be a head. So what is the PMF? 1 minus p times p. This is clear? Is this clear? Okay.
Yeah.
Now we can generalize, right? When will x1 equal to j? When will this event happen? This happens if you get consecutive. Yes.
Sorry, sir. Sir, this x1 is equal to 2 if and only if you said that z1 equal to 0 and z2 equal to 1, no, sir? So, but sir, according to the graph, sir, if x1 may be equal to 2, if
Okay,
and only
so
z1 equal to 1 and z2 equal to 1, then?
So sorry, can
then
you repeat?
Yeah, suppose sir, z1 equal to 1 and z2 is equal to also 1. Then also I think we get x1 equal to 2. As sir, at the after 3, sir, you have just taken the constant graph till say some z equal
So
to
let's
4,
revisit.
5.
So maybe my nomenclature could be slightly wrong. So when will x1 be 1? Okay. So
X1
think of it as like I'm going to toss the coin at certain time instant. Okay. Is that
So
fine?
instead of this kind of the stairs graph, sir, we can just make it, sir, like suppose 0 and 1 graph, like its range should be only 0, either 0 or 1. Like we get, sir, the x1 0 to 2, you have taken x1, no, sir. After that 2 to 3, it is x2. Then suppose again, if you are not getting, suppose you are getting till, then we can also just put down that graph like only 1 0, sorry, 3 to 4 0. Then again, if gets head, then it again goes to 1, like this,
No,
sir.
no, no, no. So it's not like that, right? So let me put it this way. So forget about, okay, let's shift just to match this. Let's shift everything. So I'm going to toss a coin here. Okay. Okay. If it is 1, I'm going to put a 1 here. Okay. Let's
Okay,
start
sir.
everything here. Okay. So let's offset it by something. So
Okay.
0 to 1, I mean, nothing appeared. 1 to 2, if at 1, if it is a head, then somebody will appear. Otherwise,
Yes,
nobody
sir.
will appear from 1 to 2. 2 again, I will toss, I'll get Z2 and so on. Okay. This is
Yes, sir.
Z1, this is Z2, this is
Hmm.
Z3 and so on. Okay.
Hmm.
Is this fine?
Yes, sir.
Okay. So is this clear? I don't know who asked this question. So the geometric about this. Is it Ayush?
Yes,
Ayush?
clear. Yes,
It's
sir,
clear?
clear.
Okay. Okay. So now this leads to a geometric random variable, right? So now let's look at what will happen. So if you look at this sum, right? Okay, I'll ask you. You should tell me the answer. Suppose I look at the sum. So sum of Bernoulli random variables. So for example, I equal to 1 to n zi. So I'm just adding all the n random variables zi, right? So geometrically, what does it mean? So I'm adding z1, here it is 0. I'm adding z2, which is 1. I'm adding z3, which is here, and so on. So if I take, for example, this is n, okay, maybe I'll use a different color. This is n, right? If I look at the height, right, what will be the height?
XN.
Sn, right? Not xn. Oh, I think I made a mistake. So forget about this. This is not xt. So notation wise, it's incorrect. So this is Sn, right? Do you agree? Because
Yes, sir.
this is what? This is nothing but Z1, Z2, right? So in fact, it's Z2 plus Z1, right? This is nothing but Z3. This is nothing but Z4. Sorry, this is not Z3. In this case, it's Z3 and so on. You are adding them, right? So this is Zn, right? In fact, Zn minus 1 if this is n minus 1. Okay? Is this fine?
Yes, sir.
So the sum will give me the height of the graph, right? So now the question would be, what is the PMF of this? The probability that at the nth time instant, there are k people in the queue. That's what I'm asking, right? So how will you solve this problem? So you have this, right? So let's say 1, 2, and so on. This is n. So you should have k arrivals, right? That means I'll put an arrow mark if there is an arrival, okay? So you should have 1, 2, k minus 1, and there is a kth arrival. So that means in the remaining time slots, you will have 0 arrival. That means the outcome Zi will be 0, right? That means you should have k heads in n tosses, right? This is equivalent to k heads in n tosses. So that's nothing but out of n, you should get k. There are n choose k ways. And each one of them will appear with the probability p power k, 1 minus p power n minus k. Okay? Is this fine?
Yes, sir.
Okay. So this is the probability of Sn is equal to k. So what is this called? for example, any random variable Sn with this PMF is called what? Binomial, right? Binomial PMF. Okay, is this fine?
Yes, sir.
Okay. Now I can I'll state one. This is the first important result that I will state, and maybe we will prove this later. So let me first state the first theorem of this course. Okay. So let's assume that Sn is binomially distributed. So binomial, I'll write it as BIN, of with parameter p. That means if you look at the distribution of Sn, the PMF looks like this: n choose k, p power k, 1 minus p power n minus k. Okay. So now and let you define this. P tilde is k by n. Okay, is this fine? So I'll just define it as P n tilde, because what is this, by the way? K over n?
It's a probability, sir.
It's not a probability, right? I'm just taking k, some number, by n. Right? Let me not write it as P subscript n. Let me just denote it by P tilde n. So essentially, this is some ratio, right? So, for example, if you observe k heads in n tosses, this is an estimate of the probability, right? This is how you estimate. Okay. Then
Okay, sir.
you take any k, for example, such that this happens: P tilde n is less than or equal to n minus 1. Okay. So P tilde n is what? This is same as 1 less than or equal to k less than or equal to n minus 1. So, okay, fine.
Yes, sir.
Then for this, probability of Sn equal to P tilde n. What is P tilde n? K. That means I am asking what is the probability that I observe k heads in n tosses, where k is any number between 1 to n minus 1. Okay. This is upper bounded by square root of 1 by 2 pi n p tilde into 1 minus p tilde. Okay, times exponential of minus n, so d p tilde and p. Okay, I'll talk about what this d p tilde p is. Okay, and this is greater than or equal, greater than 1 minus, okay, 1 by 12 np tilde into 1 minus p tilde square root 1 by 2 pi np tilde into 1 minus p tilde times exponential of minus n. Maybe I'll write it in the next step. So times exponential of minus n d p tilde p. Okay, so I'll just write what is where. So d p tilde p is defined as p tilde ln of p tilde by p plus 1 minus p tilde ln of 1 minus p tilde divided by 1 minus p. Of course, you can prove that this is greater than or equal to 0. This is called the Kullback-Leibler distance. Okay. Is this fine? Okay. So, any questions?
No, sir.
So, what is this saying? So, this is nothing but it's saying if you toss the coin n times, a Bernoulli coin n times with whose bias is p, then the probability that you observe k heads in n tosses is less than something times exponential of minus n Kullback-Leibler. It's greater than something which is slightly more complicated times exponential of minus n d p tilde p. So the Kullback-Leibler. So essentially the summary of this is the probability that you observe k tosses in n trials, right? It goes as, well, I can just directly write exponentially goes down with the n, the number of tosses, and the rate at which it goes down is given by the Kullback-Leibler distance. But there is some constant which is basically the square root, right? So the square root of 2 pi np tilde, let me write this, square root of 1 by 2 pi np tilde 1 minus p tilde. Okay, this notation essentially means that if you look at asymptotically what is happening, so this, the rate at which this thing goes down to 0 is described by this, right? That's what it says. In other words, if you take the ratio of this to the right hand side as n goes to infinity, you get 1. Okay, and here p tilde is something that is between 0 and 1. Okay, let me not write it as k, I'll just follow this p tilde because n p tilde is nothing but k. Is this fine?
Yes, sir.
Do you know, can you guess how to prove this? Any guesses? Any guesses? So, for example, what is the exact expression for this? It's n choose p tilde n, p power p tilde n, 1 minus p power 1 minus p, n minus n p tilde, this is 1 minus p tilde, right? This is the exact expression. Now I'm proving an upper and lower bound. What do you think is happening here? Can somebody guess what is n choose k? What is n choose k?
So in terms of factorial, sir.
Yeah, so Himanshu, can you tell me what is n choose k?
It's just a factorial and divided by factorial n tilde p.
No, I'm asking n choose k. What is n choose k?
Number of is
okay, can somebody tell me? Come on, you should know n choose k, right? What is n choose k? Definition
Yes,
in terms of factorial.
So n factorial over k factorial into n minus k factorial.
N minus k factorial, right? Okay, can somebody tell me what is a good approximation for n factorial?
N factorial.
Okay, that will be a homework for you, reading exercise. You should figure out what is the right approximation or what is good approximation for n factorial. Okay, so this turns out to be an important quantity. It's called the KL divergence or Kullback-Leibler distance. Well, it's not really a distance, it's a pseudo distance. It's not distance in the strict sense. For example, you can think of this as distance between p tilde and p, but distance between p tilde and p is not same as distance between p and p tilde. So it doesn't commute. Therefore, it is not a distance. Okay. Fine. We will revisit
Yes,
this
sir.
result that the probability scales down or goes down as n goes to infinity. Whenever, so at the rate exponentially goes down, but the rate of convergence is dictated by the Kullback-Leibler distance. That means if your p tilde is not close to p, right? So p tilde, you can think of it as your estimate of the probability of head. That is, you just suppose you allow k to be equal to the number of heads and n to be the total number of tosses. K over n is an estimate of the probability of head to occur. So if the estimate, if that estimate is not close to p, that means the Kullback-Leibler distance is large, then the probability of observing so many heads goes down exponentially fast. So whenever p tilde is close to p, this exponent is very small, so the rate at which it's going down to 0, it becomes very slow. So asymptotically, if p tilde is close to p, that is your true, your estimate is equal to the true value, then the Kullback-Leibler will be 0 and exponential term will go away, it will vanish, and the probability will become 1. Okay. Anyway, so we will revisit this again.
I have a
We'll see
question.
how. Yes, yes.
Sir, using this bound, are we trying to estimate how close like p tilde is to p? Just does this is the use of this bound or something else?
No. So this essentially says that unless this p tilde is close to p, right? If n is sufficiently large, for example, unless p tilde is close to p, perhaps equal, then this probability is 0. Okay. Okay, let me give you an example. Suppose you toss the coin 100 billion times. Fair coin, for example. Okay. If it's a fair coin, p equal to half, right? Do you agree?
Yeah,
Do
yes,
you agree?
yes.
Yeah. So if your p tilde is not equal to half, for example, okay, let's say you are taking p tilde to be equal to, let's say, some 0.3. So d 0.3 and 0.5 will be some positive number because Kullback-Leibler distance is positive. Now what do we have here? It's exponential of minus n. N is 100 billion times some 0.001 or whatever, right? So that is astronomically small. I mean, not astronomically small. N times that will be astronomically big. So exponential will be, very, very, very small, almost 0, right? So that means both the terms will be almost 0, right? Upper and lower bound. So the probability that, so what is p tilde? Okay, let me write it here. This is 0.5 and your p tilde turned out to be 0.3, right? If it has to be 0.3, that means you are saying out of 100 billion tosses, 0.3 times 100 billion, which is 30 billion, right? 30 billion times you observe head. That's what you're saying, which is not correct, right? If the bias of the coin is 0.5, it'll be close to 50, right? So if that means this is not 0, right? It is not close to 0. It has some value. Then the probability of you observing 30 billion heads in 100 billion tosses for a coin which is unbiased is 0. That's what it says. Well, not exactly 0, but asymptotically it goes to 0. Is that fine?
Yes, sir.
Okay.
Somewhat. Yes, sir. Yes, sir.
Okay. This tells you the penalty for making a mistake in your estimates. Okay. Okay. So, so we will revisit this particular stochastic processes later. We will study these things in great detail. So let me just go over to probability expectations. Okay. So expectation. Okay. So how do you define an expected value of a random variable? So for example, x is random variable with some PMF Px of k, let's say. This is the PMF. So I'm looking at the discrete random variable. So expected value of x is defined as you sum over all x Px of x, right? This is how you define the expected value. Why is this? Well, that's how you compute the average of a class or whatever, right? So I am assuming that everybody knows what this is. Is that fine? Is it fine?
Yes, sir. Yes, sir.
So, of course, this is a valid definition provided it exists.
So it is actually the mean. Oh, sir, I
It's
think.
the mean, yeah. It's called the mean, right? The true mean. It's also called the true mean.
Okay.
Okay. Is this fine?
Yes, sir.
Okay. So, provided it exists means that it can diverge to infinity, for example, or minus infinity. So, in that case, we say that it does not exist. Okay. Okay, so let's look at an example. Okay, so let's look at an example where certain things will go wrong. Okay, so you take. Okay, can you give me an example where the mean is? Can you give me an example of a random variable whose mean is infinity? Hmm? Can you think of an example? See, you should have a valid PMF. That means you have to describe the experiment. You should tell me what is the PMF or the probability for which the average is infinity. Yes. Can somebody tell me? Are you guys there? At least.
No, sir, I'm not getting it.
Now, you should define a random variable. That means you have to define a random variable with its PMF such that the average, the true mean is infinity. Is it possible, by the way? Can you have an experiment where the average is infinity?
Exponential increasing function.
Exponentially increasing. What is exponentially increasing?
If random variables f of x is there, whose value is e power x.
No, I didn't understand. So x is a random variable. You should tell me what is the PMF. Can you describe the
PMF is whose PMF is e power x.
Can that be a PMF? Suppose x equal to 2, then you are saying e squared, right? E squared is greater than 1. Can you have a probability of something greater than 1?
No, sir.
Can somebody tell me? Think, you want this sum to be infinity, right? When will this sum be infinity?
Sir, if you can define the Px of x like, sir, 1 by n scenario, like, sir. Something
Okay,
like
so
that,
let's,
so that we can make it divergent, sir.
So now, okay, let's say attempt 1. Okay, so whatever Sumit is saying, right? You are saying x is distributed as Px of x, which is 1 by x. Let's assume x to be positive. Okay, so belongs to n, not including 0. Okay, you are saying this is what it is, right?
Yes, sir.
There is some problem here, right? So if you sum over all x, Px of x, you should get 1, right? What do you get here?
Yeah.
You get infinity. So this
Yes,
is
sir.
not a valid, not valid,
PMF.
right?
Yes, this PMF
Now,
is not valid.
okay, you are in the right direction. Now, what do you do? First of all, you should somehow ensure that this is a valid PMF, right? What is the modification? You are right, Sumit. You are in the right direction now. So, can somebody attempt to modify this so that you get the right PMF and also the mean to be infinite? Ayush, can you attempt? Hey, have a discussion. It's okay, man. So don't be shy or whatever. So you just try. Think. Looks like today Rishabh is very silent. Can you attempt?
Sir,
Huh.
sir, actually, suppose sir, if I am taking 1 over x square, okay, sir, and just pre-multiply this by some 4 upon
Okay.
pi square, then sir, maybe this sum will get
Okay.
cancelled
So
and it will
fine.
give you a 1, I think.
Let's try whatever he's saying. So yes, he's saying 1 by x squared. Again, summation over all x 1 by x squared is not 1, right?
No, sir, pi square by 4. So, sir, I'm just trying to just multiply
Okay,
it by some
so you are
to
saying,
make it 1.
more precisely, you are saying px of x is equal to pi by 4, 1 by x squared, right?
Pi square by 4.
X not equal to 0. That's what you are saying, right? Is that correct?
Yes, sir. Pi
Pi
square
squared,
by
right?
4. Yes, sir, pi square.
Because when you sum it, right? So summation over all x from 1 to infinity, I'm saying, okay, so probability of x equal to 0 is 0. That's how I'll define. Okay, so px of x
Yes.
is nothing but pi squared by 4 summation over all x equal to 1 to infinity 1 by x squared, which
Yes,
is
sir.
pi squared by 4 into 4 by pi squared. I'm assuming it's 4 by pi squared. I don't know. I don't remember. So it's 1. Anyway, it's finite, right?
Yes,
Whatever.
sir.
So it's a valid
Uh,
PMF. Do you agree? He has
I also
assigned.
got
Sorry.
one. So like if px of x is root pi into e power minus x square. Like,
No. Hold on. So this is a discrete random variable, right? Are you doing the right scaling?
so like, the summation of e to the power minus x square
Huh?
is I don't know exactly, but is it a root pi?
No,
Like that?
no. Integral is something like root pi. Maybe I'm off by some small constant, but yeah, pi will appear there, I'm sure.
Okay.
Okay. Anyway, you are right. I mean, you can do some scaling there also, right? This is a valid thing. So now let's look at what is the expected value of x. Okay. So I should
Yes, sir.
do this, right? X equal to 1 to infinity because px of 0 is 0 and px of x equal to 0 for all x less than 0 also. Okay, let's assume this. So now you have x. Px of x is what? 1 by x squared, but you have pi squared by 4 outside. So x
Yes, sir.
cancels,
So it
this
will
is infinity, right?
infinity. Yes, sir.
There is another small modification that the textbook has. For example, the textbook, he defines px of x equal to 1 by x times x plus 1, x greater than 0. This also works. Okay? Is this fine?
Okay, sir.
Okay. Now,
Yes, sir.
suppose, let's look at again discrete. X is greater than 0, okay, non-negative random variable. Of course, I'm saying this event x greater than 0 occurs with probability 1, okay. Now let's look at what is the expected value of x. Let's also x belongs to 1, 2, etc. It's a set of natural numbers. It takes x equal to 1 to infinity x px of x, right? This is the definition. Okay, let's start writing this. Okay, so this is what x equal to 1 is px of 1 plus x equal to 2 is 2 into px of 2 plus 3 into px of 3 plus and so on, right? This is what we have. Okay, I can rewrite this in a slightly different fashion. Okay, so I can write this as px of 2 plus px of 3 plus and so on. Okay, but now I have left out px of 2, right? Px of 2 plus px of 3 plus and so on. I have left out, well, px of 3 here, right? Px of 3 plus and so on, plus px of 4 plus and so on, right? I can write it like this. Is this clear? See, this 2,
Yes, sir.
I'm considering it here, right? These two. 3, I'm considering it as like this and so on. So let's look at what is the first one. First one is nothing but x equal to 1 to infinity px of x. Do you agree? What is the second one? X equal to 2 to infinity px of x and so on, right? This is how I can write. What is this? This is nothing but probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3 and so on. This is nothing but probability that x is greater than 0, right? Because greater than 0 means equal to 1 is included. This is nothing but probability that x is greater than 1 plus and so on. So I can write this as summation n equal to 0 to infinity probability of x greater than n. Do you agree? Is this
Yes,
fine?
sir.
Yes.
Yes,
Right?
sir.
I can write this in that fashion. Do you agree? Okay. So that means for a non-negative random variable, I can write this in this fashion, or I can just do n equal to 1 to infinity probability of x greater than or equal to n. Instead of equal, greater than, I'll have greater than. This is true only for, this is very critical. Okay, so this thing is very, very critical. If this is not true, then you cannot write it the way I have written. The expected value of x.
Yes, sir.
Fine. Okay. Now I can define the expected value for a continuous random variable. So let's look at this. Let x be a continuous random variable. Then expected value of x, how do I define this? I can define this as integral, I'll take from minus infinity to infinity, x fx of x dx. So fx of x dx, fx of x is basically the PDF of x. Okay, we have seen what PDF is, right? This is how you can write. Okay, so note, this will be a homework problem for you. If x is greater than 0 with probability 1 with PDF fx of x, well, with you don't even need PDF, with the CDF fx of x, then expected value of x is equal to integral from 0 to infinity 1 minus fx of x dx. Okay, 1 minus of fx of x is nothing but probability that x greater than x. Same thing. So for positive or non-negative random variable, when for discrete, it's sum mode overall complementary CDF, right? So it's probability of x greater than n, which is 1 minus probability of x less than or equal to n, which is nothing but the 1 minus CDF, right? Similarly here. Is that fine?
Yes, sir.
Okay, right? Okay, right? Now, can you come up with an example of a continuous random variable whose expected value of x is infinity? The mean does not exist. Yes?
Sir, need to think, sir. Let me just.
Yeah, you guys should think. Rishabh, are you there?
Yes, sir.
Can you think? Can you tell me what will be the random variable x with the description of the PDF whose mean is infinity?
I'm thinking, sir. So I have to think.
Yeah. Same logic, right? So whatever you did previously, same thing. It works.
Sir, e power minus x.
E power minus x is what? It's a perfect. Oh, it has all the moments, right? In fact, well, mean obviously exists for that. Who said e power minus x?
Me, sir. Jayan.
Okay. So why do you think e power minus x is the right choice?
The mean value exists. No, sorry, sir.
Exponential. I am assuming that you are describing that for x greater than or equal to 0, right? If x is less than 0, then this is not a valid PDF, right?
Yes, sir. Yes.
Yeah. So what is the answer? We can do something like what we did, right? So we took 1 over x into 1 plus x kind of thing. Of course, x should be greater than or equal to 1 here, but I have to do some scaling c so that integral is 1. Okay, where c is nothing but integral 1 to infinity 1 by x into 1 plus x dx. I don't know what is the value, right? Well, it's c inverse is that, okay? So that when you integrate them, you get 1. Now, what happens to x integral x fx of x dx 1 to infinity? It will be 1 over x 1 plus x dx, which is integral 1 to infinity 1 by 1 plus x dx. What is this? Right? It diverges, right? This integral diverges. Do you agree?
Yes, sir.
Yes, sir.
Yeah, it's straightforward, right? It's not very very difficult.
No, sir. Actually, I'm thinking about the 1 upon x into 1 plus x, no, sir. Sir, if it is a PDF, then sir, it's a whole integral minus infinity to infinity. It must be equal to 1.
No. Okay, so okay, so I think when I said this fx of x is 1 by x into 1 plus x. Of course, c x greater than or equal to 1, 0 otherwise. This is this is the PDF. Okay, it's not.
Yeah, sir.
To be very precise. Okay.
Yes, sir.
So of course you found the mean. I mean, mean will tell me the average, right? Where this if you collect lot of samples, where these samples hover around, right? It says, well, on an average it is 0 or it's infinity and so on, right? If it's infinity, that means there is a good chance that you will get numbers which are like very, very large, too big to handle, right? If it is finite, that means that on an average there is a chance that you will get a very big number when you sample from that distribution. That means when you conduct that experiment, you might observe a number which is really, really, really big, but the chances of such number occurring is so small that on an average in your lifetime you will not observe those numbers. That's what it says, right? So similarly, I can also look at what is known as the other moments, like for example, the second moment, the variance, the standard deviation, the third moment, the third central moment, and so on. Okay, so which we will look at in the next class, and then we will also look at what is known as conditional expectations and few other things in the next class. So once we do that, then we will look at some basic inequalities like Chernoff, Chebyshev, all those inequalities, and then we'll look at convergences like almost surely, almost everywhere, all these things, and then we will start the actual, the one of the important random processes. Okay, is that fine?
Yes, sir.
Yeah, with this I'll stop. We will look at this in the next class. So, by the way, for those who are looking at it from a completely mathematical viewpoint, so for example, what is fx of x times dx? Very, it's very, very sloppy and crude. What is fx of x dx?
Probability.
This is f of x.
Mhm.
This is dx. So the height is f of x, right?
Yes, sir.
Dx is width. Fx of x is what? Area, right?
Yeah.
What will the area under a PDF curve will give you?
Sorry, sir.
If I look at the area under the PDF curve, what is the interpretation of that? Area will give you what?
The probability in the
Probability, sir.
particular interval.
So probability of x falling in this interval, right? So that
Yes, sir.
probability is very small, so I can write it as P of x, right? dP of x. So some people, I mean, the interpretation is quite different. I can say this is the probability that x falls in a small interval around this small x, whose interval is very small. So that's the probability. So this is, people interpret this as some other integral. Okay. Now you don't need the density to exist. Even if it doesn't exist, still I can ask what is the probability that x falls in some small interval. Well, there is an answer, right? You always have an answer, even if density does not exist. So this is another interpretation of this integral. I think Sumit, you are going through measure theory, right? I hope he has started
Yes, sir.
with some basic things, so he will look.
Yes.
He will definitely study this.
Okay, sir.
Yeah. So yeah. So another quick thing. So can we? Okay, I think this class is fine. I was thinking if we can prepone this class to morning, but this class is okay. Fine. Okay.
Okay, sir.
Yeah. If there are no questions, then I will stop. So I think homework is online, right, Savan?
Yes, sir. I gave it to everyone. I mean, like appears I uploaded the.
So I hope you have everybody is accessing Piazza and you are looking at the updates there.
Yes, sir.
Huh? Everyone, Ayush,
Yes, sir.
Jayan, Nitish, Shimanshu, Praveen, Rishabh. Okay. Where is Chandramani? He is not there, right, today? Okay.
Yeah.
Okay. So, Savan, just keep looking at Piazza. If there are any questions, you can post it there. Savan will keep looking at those posts, and he will try to answer. And if, still
If
there
anyone
are,
posts a question, it comes as a notification goes.
yeah, not it will come, but I request Savan to keep track of it, because I'll get so many emails, and then in between I'll get these notifications, not just from this course, from other courses as well. So it becomes difficult for me to handle. So I just try to answer. Savan will try to answer. If not possible, then you can just discuss it over here or offline, whatever. Okay.
Okay, sir.
Yes, sir.
Yeah. Okay. Thank you. So I'll stop here.
Okay, thank you, sir.
Thanks. Bye.